Good morning, dear students, and welcome to this video, which is brought to you by Educall. And please, for those new on this channel, don't forget to subscribe because subscribing encourages us to produce more content for you guys. So we count on you for that. So we are going to continue with our previous lesson, which we have continued, which is still going to be vectors. But this time, we're going to be taking the vector equation of a line. So we're going to see more about vector equations of a line, parametric equations, Cartesian equations, and angle between vectors. So notwithstanding, what's the vector equation of a line? The vector equation of a line actually has a general form of r, where r is a position vector, and a plus lambda b. And we need to know that here A is a fixed point while B is a direction vector containing a parameter lambda. Knowing I said A is called the position vector and B is called the direction vector. Notwithstanding, let's take an example to actually understand how to place this. So we're asked to find the equation of a line parallel to the vector 2i plus 3j minus k and contains the point A, where A contains 3, 5, and 6. So how do we write it in the form of an equation of a straight line? So we'll see that here. So the solution to that is that firstly, we have to identify which one is the position vector and which one is the direction vector. Now the total of the line is parallel. It is parallel, therefore the parallel there indicates that it's a direction. Because how do we know something is parallel perpendicular? Due to the direction of something. So actually, obviously, know that what A is now going to be the position vector containing the points because the points are fixed. Therefore, that is specific position in the line. Therefore, they contain those points. And B now, since it's parallel, is obviously going to be direction vector. And simply represented using the equation of a straight line, we would just apply that. And that is all about it. Next, we are going to take the Cartesian equation of a line. The Cartesian equation of a line is actually related to the parametric equation of a line. And here I'm going to be teaching you guys how to find it. You really see that it is pretty simple. So starting with it, we have to analyze the equation of a straight line. That means we simply need to analyze the equation of a straight line. Like, let's take the same example as above. I will try to find both the Cartesian and the parametric equation of this line. So firstly, you have to factor the I and J components in both the position vector and the direction vector. Here I'm going to do it simply as such. That means I'm going to take the 3i, I'm going to take the 3i here in this place and the 2i plus the lambda, you don't forget, you factor it as I. You take the 5j plus the 3j, and then you don't forget your lambda still and take the k. Same as that, as simple as that. So next, what do you do next? Now, knowing R component, you know very well that the R component is a Cartesian space with 3 dimensions, x, y, and z. Now the equation can be written as follows. Exactly. Now after that, you can simply write it as this. Now the parametric equation is simply you now taking each component and equating it to its own position. Hence, we're going to have the equations as follows. X is going to be 3 plus 2 lambda, y is going to be 5 plus 3 lambda, and z is going to be 4 minus lambda. That is as simple as that for the parametric equation. Now you see, call it parametric equation because it has parameters lambda, lambda, lambda. Now to get to the Cartesian equation, we actually need this parametric equation. Now, the Cartesian equation. The Cartesian equation is simply you doing what? Writing using the parametric equation. Will simply do what? Make lambda the subject of the formula of all these equations. So starting from equation 1, which is x, we're going to have that we're going to have x minus 3 on 2. Then in y we're going to have y minus 5 on 3, and in z we're going to have z minus 4 on negative 1. All is equals to lambda, and hence is termed the parametric the Cartesian equation. Sorry for that. Now let's get into detailed things. Understanding that we know a lot already, so let's get into pairs of lines in space. Now we assume there are lines actually in space, though we can't see them, or things are constructed using lines, and actually we call the environment our space. Now two lines in space are such that what either they are parallel or not, or they intersect or not. You need to keep that in mind because that's what we're going to be analyzing along this course. Either the lines are parallel or not, or they intersect or not. So lines that do not intersect are called skew lines. Take note of that. Lines that do not intersect are called skew lines. When the lines intersect, what does that actually mean? That means the direction vectors, either the direction vectors pass each other, either they touch, either anything, they're supposed to intersect. So now, another condition for them to intersect is that what? Another one is like the first line is a factor of another. That means that simply be increased by a certain factor, which can be k, where k they represent 1, 2, 3, 4, 5, and so on and so forth. Now, another way to know if the lines are parallel or not is actually comparing the ratio of the direction vectors. That means compare the ratios of the direction vectors. So, notwithstanding, we're going to take an example to actually explain this. Now, find out if the pair of lines are parallel or not. I'll give you this line R1 equals to that, R2 equals to that. In the B part is going to be IG, that, and that. So we're going to solve these equations, and I'm going to teach you how to solve these equations, still using how we analyze the Cartesian equation of the plane, but now in a different way because we're not going to be coming out with simultaneous equations from those X, Y, and Z. So starting, we are going to have the solution of that question. So we said line 1 was that and line 2 is that. Now firstly, we first check our first conditions. Our first condition said we have either the lines are parallel if one has a scalar factor, or if the ratios are actually a factor of each other. Now analyzing this question, we see that first of all write the equation of the line, and now we notice that B, which the direction vector here is 3i minus 2j plus 4k, and B2 is going to be negative 6i plus 4j minus 8k. Now we see something very pertinent, and noticing something here, we see that one has simply been multiplied by a scalar factor, which is negative 2, and it tells us something. That means the lines are parallel because they have a certain factor 2. Hence, it was multiply R1, which is equals to K R2. Hence, the lines are parallel. Now, let's take the next example, which says R is equals to that and R2 equals to that. Now, let's firstly try to analyze it to see if it's still going to be same. Now we see here the direction vectors I, this, and this are simply going to give us ratios. 1 is to negative, 1 is to 1, and 2 is to 1 is to negative is to 3. Here the ratios are not alike. That means one is not a factor of another, or the ratios are not even the same. Hence telling us that the lines are not parallel. And so now, if the lines are not parallel, maybe the lines may intersect. Now let's try to check if these lines intersect. Boom. So now we are now going to check if the two lines intersect. So write the line 1 and line 2. We already saw that what the two direction vectors were not like having the same scale factor, or the ratio was not common. So now what we do is that we simply write the equation in the form that we're going to take this first I and equate to this lambda I. That's going to be 1 plus lambda I, and equate to the second equation, which is going to be 2 and then plus 2 mu, and it's going to be as such. That's equation 1. We do same for the second equation, taking negative 1, the coefficient which is negative 1 in the j component, and minus negative lambda, and equating into the second equation, which is going to be 4 plus mu, which gives us the second equation. And same for the third equation, we're going to take 3 plus lambda equals to 6 plus 3 mu, which gives us that. So now we have our three equations. What we're asked to find now is lambda and mu. So finding these two is going to give us a common something. So what we're going to do is that we'll just look for we'll pick the simplest one to pick. I'll take 1 and 2 and I'm going to add them together. So taking 1 and 2 and adding them together, I'm going to have that 0 is equals to 6 plus this, and simply I'll have the value of mu, which is negative 2. Now it has given the value of mu, and from there, now finding lambda from 1, I'll substitute the value of mu in equation 1, and which is going to give me lambda as negative 3. Now what do? I now take these two values, mu and this other value, and equate it into my third equation to see if it's valid. If it's actually valid, it means the two lines are going to be equal, and hence telling me that the lines intersect. So now substitute it in equation 3. It's going to tell me if the two lines are actually intersecting. So I'll have the equation 3 as 3 plus as lambda equals to 6 plus 3 mu, and now I substitute the value of lambda and that, which gives me what? You notice that I have a 0 equals to a 0, means that equal. Hence R1 is equals to R2, meaning that these two lines intersect. Good. Now here we're going to take the angles between two lines. The angle between two lines. How can we actually find the angle between two lines? The angle between two lines is simply going to denote how the lines actually intersect. That means when they intersect, did they form a certain angle between them? Obviously yes. If, let's take for example, if the lines were actually at right angle, we obviously know that the angle between them is going to be 90 degrees, because this angle there is 90. So actually this is going to be studied simply with the direction vectors. We're going to study that with the direction vectors because, as I said, the direction vector is actually what orientates the line in a particular direction. It's actually if you can use to tell if the line is parallel, if the line is like orthogonal or not. So it's going to be very important, and it's simply going to be in the form that where we're going to take the first, we'll take the first, we'll dot, we did dot product in the last video. If you don't really understand what dot product, you can go back to the last video. So we took the dot product of the two direction vectors and we equated it towards their magnitude. We dotted their two magnitudes and multiplied it by cos theta. Now to find that angle, we'll simply make theta the subject of a formula, which is now going to be cos inverse of the dot product divided by their magnitude. As simple as that. Let's take an example for you to actually see how it's applied. Now the two lines with the equation that's 2i plus 9j plus 13k plus lambda into 1 into I plus 2j plus 3k, and R2 negative 3i plus 7j minus 2k plus mu into negative I plus 2j minus 3k. Good. So solution. So what are we going to do? We've been given two lines, and now we're going to extract their direction vectors. That means the direction vector of the first is that, and the direction vector of the second is that. So what we're going to do is that we're simply going to dot them, and dotting them we're going to have negative 6. Now we find their magnitude. Having their magnitude, we dot them, and we're going to have root 14 multiplying root 14, and simply writing the what? Equation. But now look something here which is going to be much clear. I didn't ask you to find the angle, but I asked you to find the cosine. I want you to leave the answer in form of cos theta. If I ask the angle before, you make theta the subject of a formula by taking the cos inverse. So it's simply going to be cos theta equals to negative 3 on 7, as simple as that. Now if you want to find the angle between these two lines, you make theta the subject of a formula here by taking the cos inverse of negative 3 on 7. That's it. Now let's move to the vector equation of a plane. So we are in the vector equation of a plane. So we know many planes, the Cartesian plane, many planes. Like we're going to now try to see now the vector equations of planes. The vector equations of planes are simply almost similar like the vector equations of lines, but now is having a general formula where in a plane we are now going to have something called a normal represented as n. Here we are going to multiply r dot n equals to a dot n, where r here is going to be our reference when in Cartesian plane, that's x, y, and z, and a here is a point in the plane, n is a normal. N here, the normal is simply the line perpendicular to the plane, that's all. So as I said, let's take an example to see how we can apply this. So find the vector equation of a plane that is perpendicular to the vector 2i plus j minus 2k and contains the point a, 3, 2, and 4. Contains the point a. Hence, we already have the point for filling our a here. We already have our a. Now, what's left to do is our normal. They said perpendicular to this vector. Therefore, they have given us the normal because I said the normal is the line perpendicular to the plane. Simply, we have our normal and we have our plane. This example is so easy. So we'll take a solution to that. So we're going to have our normal as that 2i plus j minus 2k and our r as the reference plane x, y, and z, and a the point 3i plus 2j plus 4k. Sorry, here is a k and not a j, so I'm just gonna put a k and not a j. So I apply my formula now. So applying my formula, I'm going to have that. I'm still made the same error here. So this is a k, not a j. Good. Okay. Now I'm going to apply this formula. Hence r, you will have r as this x, y, and z. I dot it with the normal 2i plus j plus 2k, which is equals to the point a, which is going to be 3i plus 2j plus 4k. Dot it with now the normal, and dotting it, I'm going to have this. First of all is going to give me 2x plus y minus 2z. Now if I dot this other side, I'm going to have 6 plus 2 minus 8. That simply gives me a 0, and hence the equation of the plane 2x plus y minus 2z equals to 0. Now, equation through non-collinear points. Now what we previously did, the points there were collinear. Collinear means on the same line. That's why we could easily find it. Imagine we have two separate lines now. So having two separate lines now, we're supposed to do something which we did in the first video. As simple as that. Now three collinear points may be A, B, C. Now what the equation, the new equation is going to be written as this. R is going to dot what? AB cross AC equals to A, which is now it's still the same equation. This AB cross AC is still the normal. It's still the normal. That's R dot N equals to A, which can be any point now. Here now the point can be any because it's a plane. It can be perpendicular at any point or bend at any point. Therefore, you can choose A or B or C depending on you. The simplest point which can give you your answer as quickly as possible. So let's take an exercise to see this. Now the points A, B, and C have position vectors A, B, and C respectively relative to the origin O, where A is equals to I plus 2j plus 3k. I don't have a problem with k or something. Then B equals to what? 2i minus 4k. C equals to 5i minus j minus 3k. Now, what am I to do? I'll simply, since there are 3 points here, I'm supposed to firstly to find what? This common point where they are perpendicular, they are orthogonal. That's their normal. So taking their normal, I'll have to find their cross product. That means I'm going to take AB cross AC. Now, taking AB cross AC, I'll simply have negative 9i minus 22j plus 5k. And next, what am I to do? I'll simply apply my formula, simple as that. I know R is equals to x, y, and z, and then the normal AB cross AC is going to give me that equals to any point. I'll choose the point A, which is I plus 2j plus 3k multiplied by the normal again, and where I'm going to have that. Now multiplying, I'm going to have negative 9x minus 22y plus 5z equals to negative 38, and that's the equation of a plane.